Okay, this is introducing a concept, mission concept that is going to be proposed, and we're doing a feasibility look relative to the technology. At issue is that radio meso-scale features, and then whenever you're doing remote sensing of these features, then you can capture unique dynamics across broad swaths of space. We're looking at understanding these using a technique called Faraday rotation. So, uh, some of the one particular interest that we have is with respect to coronal mass ejections and how they evolve. And so, with Faraday rotation, you can make field measurements through these structures. It's an integrated measurement, so you've got to back out the information and interpret it with the models and other things. And in the meantime, whenever you say other things, I mean white light measurements, other instrument data. So the idea is that you would have four spacecraft going across the area of uh, the plasma. I'm sorry, the area where you have plasma streaming from the sun to the Earth. So it's earthbound plasma. And so we would get these observations that eventually you can observe in situ with your spacecraft parked at L1. And in the meantime, the distances, they're a little exaggerated in this figure, but the blue line that goes from M1 to M2, those are two of the spacecraft that were 0.5 AU. And where you have the X, where the signals cross going from 1 to 4 or 2 to 3, that is at 0.25. And then you've got one line between the two spacecraft that are very close to the sun. So you can get multiple observations as it crosses these different lines. Now, the question is the feasible? You have spacecraft with their limited power supply, and you do not have an infinitely large, well, not infinitely large, but you don't have a 100-meter collecting dish to work with. So you've got certain limitations on your detectability. And so we took a look at this and said, what kind of precision can we achieve, and what kind of challenges are we facing relative to the signal ratio? And so one of the issues that we found is that there's a certain amount of noise that develops. You have this just simply with the signal propagation through the plasma, but you also have instrumental noise. And then there's another noise source, which I'll talk about in a little bit. And so you get this in the electric field. And so as we looked at this, the uncertainty goes down as your signal to noise ratio goes up. Big surprise, right? So what we found is that you can get to a precision of around 8 degrees with an SNR of around 17 using this approach. So then we took another look at it and did a simulation with Monte Carlo did a Monte Carlo simulation to examine this and came to similar levels. We're still working out exactly what our noise sources are precisely to model them, but it's coming out to be a little bit more, how do I put it, detectable at lower SNRs than necessarily the theory predicts, but there's complications, and I'll show you why. So we have actual, this is plane of polarization information. So before you eliminate other instrument contributions to your signal, you have a plane of polarization. And how it changes ultimately comes down to Faraday rotation. So this is roughly approximate to the change in Faraday rotation. But what you can see is that as the SNR decreases, then the error in the plane of polarization increases. And we're going to take a look at two time periods what you can see on the right is that at the very top, there was a measurement taken in May 2014. And then at the very bottom, you can see that there's the honest to God delta Faraday rotation from 2015, February 7th. So that's what I'm showing here. The 2014 is up top. The 2015, February 7th, is at the bottom. Happy to explain main beam versus secondary side beam later. But the point is that your observation on the Earth is on a rotating coordinate system. And so that's what you have with the parallactic angle. So the parallactic angle predicts what is the rotation that you would expect to this coordinate system. And that's the red line on the left two plots. It gets a little problematic as you approach zenith. And so I wanted to point out that the top plot has crosses zenith. I did a correction so it's smooth, but this is an antenna issue, so part of the fun of calibration. However, whenever you get to the right, you'll notice that if you calculate a cumulative the standard deviation in the black line 2 times the standard deviation for these changes in the plane of polarization after you've detrended the data. So this is with the detrend. And then what you'll see is that the change in the Faraday rotation, it does get to a maximum of over 20 degrees, but the standard deviation, it tends to float around 7 degrees at a range of 1 dB SNR. And then on the 2015 data, we get to a fairly good standard deviation, 2 times standard deviation, around 2 degrees, and this is 13 to 25 dB. And so you can see that the extent reaches up to maybe 6 degrees, but it's far more closer to, has a less variability than necessarily for your instantaneous theory, it's got less variability as you look at it with more data points that have been collected. So here's the calculation of what we're looking at, and my apologies, that's not supposed to be final SNR, that's supposed to be SNR prior to post-processing. But we did some calculations about how strong our signal is, and then various contributions of noises. The issue is galactic noise power. So whenever you think about Faraday rotation, it's frequency sensitive. And so we are looking at frequencies that are around 200 megahertz plus or minus, 50 megahertz or so. And what happens is at those frequencies, the galactic noise power goes up. And so that's going to be one of the larger challenges because in the Earth's orbit, sometimes the galactic plane is line of sight, sometimes it's perpendicular. So that's why you've got some variability there. So then we found that prior to the post-processing, so that final SNR, which is processing, is around -11 to +13 decibels. So we would like to boost it somewhere around 10 to 20 decibels to a good SNR. And pulse compression gives you a good boost. So that's one of the approaches that we're looking at. So, in summary, the structures of meso-scale features can be sampled with satellite observations, but Faraday rotation enables probing this scale size with across a broader swath of space. The radio signals that we're looking at, I'd say roughly 100 kilometers in size for which the size of the plasma features that they're detecting. So, and Fetch would be, so I'm talking about this mission called Fetch, and it would be the first space-based instrument to, so both in receiving and transmitting, to do these measurements and upstream of the Earth. So you need to make these measurements and relative to the frequency, the lower the frequency, then the more Faraday rotation you would see, the higher the frequency, the less Faraday rotation that you see. And so that's why we want to understand what precision, and then if you want to boost over that amount, then you look at dropping your frequency. But with dropping your speed, there's all kinds of other issues that come into play. So that's why we're looking at around 200 megahertz. So we found that uh, a fairly good Faraday rotation measurement within a few degrees. So you did see a number, quite a bit of fluctuation there, and some of that is going to be plasma fluctuation. So there's going to be like a boundary in how much Faraday fluctuation that you're going to get. And so we would get to 20 dB so that we can measure structures such as co-rotating interaction regions and things like that. And but relative to coronal mass ejections, they're so large and coherent and strong, like fields and density, that we can achieve that precision, but we'd like to do more. And so we validated this with Monte Carlo. So we found that this is feasible with pulse compression and additional SNR processing, such as what I showed earlier with stereo, which note that the stereo data was collected with a 100-meter antenna on the Earth. So just keep in mind, those were unique data sets. And then an alternative is that we find another method for significant SNR enhancement. And so whenever I say that there are other ways of processing this, increase integration time that will boost your SNR, particularly with coherent signal. And so we haven't scoped the whole entire solution space. We see that there's a solution in sight, which is the pulse compression combined with integration. How much time did I do?
Um, about 11 and a half minutes.
Yay. Okay, I'll work on it.
Yeah. Does anybody and that was including the that was excluding the start, sorry, I started it back over is what I meant to say. Once
Yeah,
the
I got you.
lecture muted. Does anybody have any questions? All right. Well, thank you for the presentation. Um, I will go ahead and stop the recording. And thank you, everybody.